Okay, so this is the first part here of homework, or the notes for 1-4. You guys all have this on the example page, so I'm going to go through it pretty quickly. So they do have the definition here, free fall. The biggest thing with free fall is it's when only gravity is acting, so no other forces, so we'll assume that there's no air resistance. If they ever reference free fall, assume that there is no air resistance unless they tell you otherwise. So strictly speaking, free fall can only happen in a vacuum where there's no air resistance. However, if objects are small and heavy, we'll assume that the air resistance is negligible. We'll also, if we do deal with light objects, we will see that friction and air resistance are not negligible, and we'll deal with that later on in the year. So then any two objects in the absence of air resistance will fall at the same rate, unless they all experience the same acceleration. Again, hopefully most of these bullets here are review for us, but if you needed to go through it, there you go. So then the first kind of definitions that I want to start with are just going back to how did we define gravity? How did we define g? So we know the magnitude, the acceleration due to gravity here is 9.80 unless they tell us otherwise. Now sometimes on the multiple choice they'll tell you to use 10 like they did last year, but we'll assume that it's 9.80 unless they tell us otherwise. And then the reason that it's helpful to know that the acceleration due to gravity is constant is because that tells us that we can use just the acceleration as a change in velocity over time, and that also tells us a little bit of information then about the fact that we can use our kinematics equations, right? So the big thing that it's a constant tells me that I can use my VOTAT and all of those fun equations to work with. So a couple big relationships that pop up from the fact that the acceleration due to gravity, assuming we know that it's free fall, is constant. And again, we'll look at when it's not free fall later on in the year. So then the first conceptual example here, and this is something we saw several times throughout the year last year. So a skydiver jumps from a hovering helicopter. Why is it important that the helicopter is hovering? Right? Well, the important thing is, since the helicopter is just hovering, we know that it's not moving up or down, so there's no initial velocity, right? Potentially if there was some initial velocity, that could maybe change things a little bit here. But we'll assume that the initial velocity was 0 for both of these skydivers. So a few seconds later, a second skydiver jumps out, and they both fall along the same vertical line, ignoring air resistance because both skydivers are very massive little people. The reason I threw that in, other than just being odd, is because we know now that they're both small and heavy, so we don't have to worry about air resistance. So part A, does the difference in their speed stay the same throughout the fall? Why or why not? So for part A, right, does the difference in their speeds stay the same throughout the fall? Well, this all boils down to the fact that if they're in free fall, they have a constant acceleration, right? And we know that acceleration is defined as change in velocity over time. So one skydiver has a 1 second head start, which means he's going to change velocity by 9.8 meters in that 1 second, right? So here's skydiver 2. Skydiver 1 is already down here, and he's already moving at 9.80 meters per second because he's been falling for 1 second before skydiver 2 actually jumps out. But will the difference in their speed stay the same? Well, the answer to that is yes. And the reason for that, again, is because my acceleration is constant, right? And because my acceleration is constant, the velocity changes by the same amount with every second of time. So each second, these guys each go 9.80 meters per second faster. So after 1 second, now skydiver 2 is 9.80, and this guy here is still faster, but he's 19.60 because he's 9.80 meters per second faster than guy number 2 here. So anyway, the difference in their speed stays the same because they have a constant acceleration, and the change in velocity per time then is constant. So the difference in their speed is constantly 9.8 meters per second. For part B, does the vertical distance stay the same throughout their fall? Why or why not? Again, we saw this one a couple times last year, and the answer for this one is no, right? And the easiest way to represent that is think about the kinematics relationship here, where we've got our delta x equals v0t plus 1/2 at squared. We know their initial velocity was 0, so we're going to ignore that. We know their acceleration was constant, but then think about what happens every second, right? So initially, my delta x would be 1/2 a times 1 squared. But then when I plug in 2, it'd be 1/2 a times 2 squared, which is actually 4 times bigger, right? And then 3 squared, which is actually 9 times bigger, then 4 squared, which is 16 times bigger. The distance increases by more and more and more each time, right? It went from 1 to 4, which is an increase in 3. Then it went from 4 to 9, which is an increase in 5. 9 to 16, which is an increase in 7. So the distance is constantly getting longer. So even though their average speed, the separation in their speeds will be the same 9.8, the disparity between their distances is going to increase over time. And that's simply because Skydiver 1 is constantly moving faster, so he's constantly covering more and more distance than Skydiver 2. So big concepts. I know I spent a little bit of time describing that, but I do want to make sure you guys are all comfortable with some of these key concepts because they do come up time and time again. So make sure you're good with those. This example, hopefully a little bit easier. An antelope leaps straight up from the ground, extending its legs forcefully and accelerating at 35 meters per second squared for 0.70 meters as it straightens its legs. Once its legs are fully extended, it leaves the ground and rises into the air. How high does it go? Okay, so really all this comes down to is it's a projectile problem where something's going straight up in the air, right? And in order to figure out how high it goes, we need to know what its initial velocity is. So that's the reason they gave me all this background information. So there's really two parts of the motion here. There's part one, right? There's part one, not parts one, where the antelope is accelerating upward, and then there's part two where he's in the air, and so he's essentially in free fall, right? Because once he leaves the ground, the only thing acting on him is gravity. So as he accelerates upward, as he's in free fall. Well, as he accelerates upward, we know his initial velocity was 0. We want to find his final velocity so we know what speed he'll leave the ground with. And then we know the acceleration is 35 meters per second squared, and the distance here they gave me that he compresses or that he extends is 0.70 meters. So I've got enough information then, right, to find my final velocity. So I can use v squared equals v sub 0 squared plus 2a delta x, and I can solve for my final velocity. So obviously just setting this up and then calculating. This actually works out very nicely to be 49, and then the square root of that, obviously. So my final velocity is 7 meters per second. So again, the reason this is important is this now tells me my initial velocity that the antelope left the ground with. So he left with 7 meters per second. We know the acceleration once he's in the air is negative 9.80 meters per second squared. And it is important that if I've defined the initial velocity as positive, his acceleration better be negative. And then this goes back to what we saw a lot of last year. The key to these problems, right, is a lot of times breaking it up halfway through. So I know that when the antelope reaches his highest point, his final velocity at that location is 0. So again, the reason I threw this question in, just to make sure we go back and revisit that fact. I know that at the highest point, the final velocity is 0, which is good because now I have 3 pieces of information. So if I want to find delta x, I just use the exact same relationship, right? But this time I'm solving for delta x instead of v final. I know the final velocity is 0. I know his initial velocity is squared, so 7 squared, plus, and once again here you can see where it's important that I keep this to be negative 9.8. Otherwise I'd end up with a negative displacement, which would just mean we've defined going up as negative. But anyway, so I've got that information set up, and then obviously just solving it from here. So just calculate that. So then when we solve for the delta x, we should get about 2.5 meters. And actually I got exactly 2.5. So anyway, this would tell us how high he went from where he left the ground, right? So this would be 2.5 meters on top of his initial height there. So if you were actually looking for his the highest point he reached, you would actually make an argument maybe that he went up to 3.2 meters. But this is how high he got off the ground from where he left. So anyway, hopefully this example is pretty easy, right? Mostly review for us on this one. This example also hopefully is pretty easy. It is one of the more complex review questions from last year. But still, that being said, hopefully we'll agree that these type of questions aren't too bad as long as you remember the key of breaking the problem up at the top. So I'll let you guys read through it. Obviously you can do that. We've got our building, which we're throwing it up from, so I'll just sketch the picture here. So my building is 50 meters tall. The guy throws it up with an initial velocity of 20 meters per second. They ask us what is the total time that the stone is in flight and what is the impact velocity when it strikes ground. So this is one of those situations in which we're assuming that it's going straight up in the air. It goes up, reaches its highest point, and then falls straight back down, but misses the building and then falls down to the ground. Okay, so we don't have to worry about any horizontal motion here. We're just strictly looking at moving straight up and down. So again, the key to these type of problems, if I want to find the total time of the stone's flight, the key that I usually work with is I want to find the time it takes to go up and then the time that it takes to go down. Okay, so if I want to find the time that it takes to go up, think about the measurements that we know. We know the initial velocity would be 20 meters per second. The final velocity at the very top there would be 0, right? Because again, I'm taking advantage of the fact that it momentarily stops. And then the acceleration is negative 9.80 meters per second squared. So at this point, I've got 3 of the 4 pieces of information, so just solving for time. And obviously, I can use a nice easy VOTAT for this one. So I've got my final velocity, my initial velocity, negative 9.8, and then t. So solving for the time that it takes to go up, right? It's just going to end up being 20 divided by 9.8. So obviously a little bit more than 2, about 2.04 seconds. So this is how long it takes to go up. I've answered about half of my question, but I still need to do a little bit more. So then, I know last year we looked at this and talked about this a little bit. If you doubled that time, you'd find out how long that took to reach that same height again, but that's not particularly helpful for us because then you have to fall all the way back down. So instead, right, the easiest route to go is let's figure out how high it went above the building so that then we know the total height that the stone reached, and then we have the acceleration and the initial velocity, which makes falling down a little bit easier. So then to find the time that it takes to go down, again, the first thing I'm actually going to find is how high it went up. So I'm going to use the same information to find out the height that it reached. So I'll use, again, you could use any of them at this point, but I may just jump back to this one since these were all the original measurements that they gave me. So I've got 20 squared plus negative 19.6 if I go ahead and multiply that by 2 and then times delta x. So again, 400 divided by 19.6, and I get that it reaches a height of about 20.4 meters above the top of the building. So then that tells me my total height, right? So my total height here, my total delta x is 50 plus 20.4, so 70.4. And then I know my other measurements as well, right? I know that my velocity at the very top up there was 0, so my initial velocity is 0. I'm going to go ahead and define the acceleration as going downward, and we'll see a few instances where we don't want to flip back and forth with the acceleration being negative and then positive. But again, because I'm just breaking it up at the top, I'm going to go ahead and define that as positive acceleration. And then obviously here I'm looking for the time and I'm looking for the final velocity for part B. Okay, so for part A we need to finish that out first by finding the time. Hopefully that's not too bad though, right? We can just do delta x equals v0t plus 1/2 at squared. Again, at the top of the path at 0, so 70.4 equals 1/2, so 4.9 t squared, and then solving for that. So then I get the t that it takes to go down. The time that it takes to go down is 3.79 seconds. So then to answer part A, right, I've just got to total up those two times. So 2.04 was the time that it took to go up, plus the total time that it takes to go down was 3.79. So then adding those two up should be about 5.83. Depending on obviously where you've rounded off, it can vary a little bit, but it should be pretty close to 5.8 something. So then for part B, just finding my final velocity, and again at this point you could use any of the means. You could use VOTAT or do whatever method you are the most comfortable with. But I will just use VOTAT since I now know that it fell down, and keep in mind I'm only using the time that it takes to fall down. I'm not using the total time. And that's the biggest mistake to watch out for, but I'm using that and then just calculating from there. So then I got the final velocity to be about 37.1 meters per second. Okay, so again, make sure, double check your answers here, just make sure you use the time that it takes to fall down and didn't accidentally use the 5.83. We'll pick up obviously the next couple examples in the next part.